At the beginning, we set up to test different feeds coming from different geographical locations, urban centers, rural areas, and places in between.
We started out with trying different feedstocks, trying to see how they respond with our own catalyst.
And transform those into the components of sustainable aviation fuel.
When we started, we had no idea if this was going to really work or not. Now, after doing the work for several months, we've gotten to a point where really it worked better than we ever expected.
I am happy to report that the project was a success. We managed to accomplish that, and we did it on time and on budget. The catalyst, the materials that are used in order to convert feedstock into fuel have many challenges. They require fairly pure feeds. One of the main things that we found is that waste feeds such as yellow grease or used cooking oil, brown grease or grease collected from grease traps could be converted into sustainable aviation fuel. So that's one of the main findings of our work. In addition to that, we determined that feeds that come from different geographical locations can also be converted. That's one of the main innovations here, whereas folks right now are using fairly pure and sometimes expensive feeds. We can apply our technology to convert waste feeds into sustainable aviation fuel.
We tested this catalyst to see if the catalyst is actually stable and recyclable. So what we did was we looked at the possibility of having this to be done in 6 days for 2 cycles. The result we obtained prior to regeneration and after regeneration seemed pretty similar. That tells us that our catalyst is actually stable, and also it confirms the recyclability of our catalyst. That saves us time, saves us money as well.
This project was actually even more successful than we were hoping, I think, because one of the big goals was to produce aromatic compounds, these compounds that are not typically made by a lot of the processes that sustainable aviation fuel is produced through. Our results showed us that we got almost nothing but aromatics. That was a really big surprise to us. Aromatics are one of the hardest types of molecules in sustainable aviation fuel to produce. They're also one of the most important because those are actually what gives you the seal swelling quality that the fuel needs in order to not leak when you actually put it in an airplane. Sustainable aviation fuel, it's made up of several different classes of compounds: aromatics, linear alkanes, isoalkanes, all these different kinds of carbon-containing molecules with the carbons just arranged in different ways. So even if we aren't making those other classes of compounds, this was still a huge success because then we can take those aromatics and blend them with those other compounds, a blend stock, if you will, to actually blend with fuels produced by other processes in order to get something that is identical and indistinguishable from fossil-derived aviation fuel.
When we started the project, we were already very appreciative of how easygoing and helpful R&D was. At the end of the project, that did not change. If anything, it was even more clear to us that they are interested in the work, not in the red tape. It's just a great funding agency to work with.
The OUR&D project has actually been, I've actually learned a lot, to be frank, beginning with the catalyst preparation, the catalyst characterization techniques, and also testing the catalyst in the reactor. The skills I've garnered so far would better position me to seek for postdoc opportunities after my PhD. So I think I've actually gained a lot of knowledge.
I would really love to work with them again in the future because it's been unlike any funding source that we've ever worked with before. There's no red tape. You don't have to submit this report right now. You don't have to deal with a lot of the onerous qualities that a lot of other funding agencies have. This has really been a unique experience and one that I hope we can repeat again in the future. We've still got a huge amount of work to do here. Hopefully we can work with R&D again in the future to get more data like this, because this data is kind of the lifeblood of our work. We need this preliminary data in order to go get those big grants. Each one of these reactions that we do takes supplies. Making catalysts takes money. Running our equipment takes money. Maintaining our equipment takes money. So at every step of this process, we have to have that funding input in order to do the work. And so this really gave us the opportunity to generate that data that we can then take and go get more money to do more work. That's the key, is to make sure that you always have new data so that you can use that data to get more data, really dial in those reaction parameters to give us something that is indistinguishable from a fossil-derived aviation fuel.
So right now I'm just about to show you the semi-batch reactor, and it's an excellent system to perform screening type studies. However, it is not the type of system that is actually used in industry. We can use it to identify a good combination of feedstock, catalyst, and reaction conditions to then try to translate that into a continuous type of experiment. So this is the semi-batch reactor, and it's basically a glorified pressure cooker. So we can put the catalyst, any feedstock, solvent in there. We lift it so it's all enclosed. We can put this heating mantle right next to the reactor body. You can see that we have a stirrer here, and pressurize the system, heat it up, and the reaction takes place. After a couple of hours, we can stop everything, depressurize, open the system, recover the product mixture, separate the catalyst, and analyze the liquid products. But as you can imagine, all that is a pretty labor-intensive process. So it's not the best way to actually produce fuels, but it's a pretty good way of screening a catalyst or determining the best combination of feedstock, catalyst, and reaction conditions that would afford the best results. And once that we do that, we're ready to take that combination to the continuous reactor, which is the system most closely resembling that used in industry.
So the fixed bed reactor is basically a continuous reactor where you have your catalyst in the reactor and you have your feed continuously put into the reactor. So the good thing about the fixed bed reactor is that you can actually get samples at almost every time and analyze these samples so you can know exactly what's going through the reactor at every point in time on stream.
The continuous reactor is very industrially relevant. That was the big idea between running that system for this project, was just to be as industrially relevant as we can get in the lab here.
So after screening study using the semi-batch reactor, we identified the best condition as well as the best catalyst to test in the fixed bed reactor. So what we do is this: we have our feed ready, we make sure our feed stock is ready, as well as all the other required conditions, and also our gas ready for our reaction to take place. So we have the catalyst fed into the reactor, and we reduce the catalyst. And after reducing the catalyst, we make sure the feedstock is ready so we can actually have the process go through for about 6 days. So what we did was we actually carried out this cycle for 6 days at somewhere around 144 hours at 2 different cycles. So when we had the first cycle at 72 hours and we regenerated the spent catalyst and we obtained our samples, the good thing about this reactor is that we can actually obtain samples at almost every point in time and analyze these samples. So we obtained the sample over here and also the gas from this dry test meter. And when we get that, we also analyze the gas samples generated. So the good thing about this also is that we have a controller where we can actually control what's happening in the fixed bed reactor. So we have this right here, which tells us the conditions and also the variables that we are working with to ensure that these variables are also maintained. That's basically what we do with the fixed bed reactor.
Each one of these fuels that we produce has hundreds of different molecules in there. So it's essentially just a huge mess of different things for us to look at and pull apart. It takes that mess of molecules and runs them through this very long column. And by very long, I mean, I think the column we have in there right now is 60 meters long. And that column is designed so that it will actually separate each one of those different molecules out. And then once those molecules have been separated out by the column, they each go to a detector. And this machine actually has two different detectors. It has a flame ionization detector and a mass spectrometer. So the big advantage of this particular machine is that it does have those two detectors. The flame ionization detector is great for telling us how much of each one of those compounds is in there. So say you've got 10 different molecules, the column will separate all those out, and then the flame ionization detector will tell us exactly how much of each one of those molecules that we have. And then the mass spectrometer is a really important tool here because it will tell us what each one of those things is. The column will separate all this stuff out, but the flame ionization detector essentially just burns them. So you can't actually see what is being burned. You can just see how much is being burned. But what the mass spectrometer does is it will take each one of those molecules and break a few little pieces off of it, and then it will measure how heavy those pieces are. And by measuring how heavy those pieces are, we can really get a sense of what the actual molecular structure of those molecules are. That'll tell us whether it's a long chain hydrocarbon, like gasoline, whether it's something aromatic, or one of the other components that makes up sustainable aviation fuel. It'll tell us what it is, and then we get how much of it there is from the flame ionization detector. So this instrument really gives us an opportunity to deeply analyze the fuels that we produce, to say, okay, we have this much of this, we have this much of this, and we have this much of this, and sustainable aviation fuel derived from fossil sources has this much of each one of those compounds too. And then we can really guide ourselves towards a fuel that is totally indistinguishable from a fossil-derived aviation fuel. So again, this machine is what we use to actually analyze the liquid fuel that we produce. What it does is it uses this auto sampler up here to basically pick up one of these little vials, put it into the sampler here, and then you can see there's a needle in there that's going to inject that sample into the column. And once again, that column is down here in an oven. And that sample, once it gets injected, is going to go through the whole length of this column. And you can see this column is about 60 meters long when you take everything into consideration there. So it really is as long as it needs to be able to separate out all these different chemical compounds that we have. So then from the column, the sample is going to travel to the detector down here, which again is that mass spectrometer and the flame ionization detector. So what this does is kind of measures the weight of each one of these molecules and tells the computer over here how much each one of those different molecules weighs. So when you look at the computer, you can see what it spits out is this, what we would call a chromatogram. And this chromatogram essentially shows a bunch of different peaks. And each one of these peaks represents a different chemical compound, or sometimes even a mixture of different chemical compounds if the column didn't effectively separate them. So each one of these peaks, I can then call up a mass spectrum to see what different weights of molecules came out of there. And this computer will very nicely analyze that for me and give me a molecular structure of exactly what that particular compound is. So the compound that I just happened to pick there is something that's aromatic, as you can see. Just by the fact that, just by the chemical structure of it, it's one of these aromatic compounds that we need for seal swelling. So we can also look through here and find other things. Here is something that's still aromatic, but it also has another piece that's a different chemical structure. And then we can also find things that are just kind of less, not aromatic, but still a cyclic molecule. And this really just lets us get really granular into how like seeing what specific chemical compounds are actually in the fuel that we're producing. So again, this is actually our solvent here, which is dodecaine. So that's a 12 carbon long chain, and that's something that's in a lot of fuels, but that's actually our solvent here. So that's not something we made, but it's something that's still in with all the rest of it. So that's more or less the ins and outs of this machine, I think, and in terms of the data analysis and everything like that too.